So what we're going to do here is we're going to have a look at galvanic cells. So what a galvanic cell is, was also known as a voltaic cell, is an electrochemical cell that has two half reactions operating in two different containers connected by a salt bridge and a wire. So we've looked at that already in class. So what we're going to do now is we're going to look at a general solution for drawing out the cell and also calculating what we like to talk about as E cell, or the whole cell potential. So the first thing we're going to do is we're going to write out the two processes that we have here, where it is already in a notation. It says nickel metal in a 1 mole per liter nickel chloride solution. And in the other cell, which is separated by the double bar, we have aluminum metal in an aluminum sulfate solution. So we really don't know what is the anode and what is the cathode here. So what we're going to do is we're going to write out both of these equations as reductions. So first of all, I'm not really worried about the chlorine at all. I'm worried about the nickel because it's nickel metal. So instead of writing out nickel chloride, I'm going to write out just the nickel ion. And I know it's nickel plus 2, of course, because the 2 with the chlorine crosses back over to be with the nickel. So since it's plus 2, I'm going to use 2 electrons to give me nickel solid. That's the first reaction. The second one, I'm going to do the same thing. Instead of aluminum 2, I'm going to write aluminum plus 3. And it will take 3 electrons to bring that back to aluminum metal. So I have both of those processes listed. The next thing that I have to do is I have to get what we call their standard reduction potentials. So we write E standard reduction, E standard reduction. And where we get those is in our Appendix E. So we have this booklet, which is listed as Appendix E. And what we're going to do is we're going to find the two reactions. So right off the bat, there's the aluminum one, aluminum plus 3 electrons to aluminum solid. And that has a reduction potential of negative 1.66. So we write that in, negative 1.66, and the unit is volt. The other one I'm looking for is nickel. So I'm going to find nickel somewhere on here. Nickel plus 2. And it is negative 0.28. So all I've done so far is I've taken those two expressions and wrote them out as half reactions. The chlorine in the nickel chloride does not actually factor in at all, and the sulfate does not actually factor in at all either. So what we'll look at is we'll try and figure out which one will undergo reduction. And the way that we know that is by looking at the standard reduction potentials. The one that is the most positive is going to be the one that undergoes reduction. So this means that this is reduction, leaving that one to be oxidation. And oxidation means this is going to be the anode, and this is going to be the cathode. Close that up. So cathode and anode. Again, we know that the one with the more positive standard reduction potential will be the cathode. And I would say the big challenge here is just making sure that you can write out the meaningful half reaction. So we're going to write out E cell is equal to the standard reduction potential at the cathode. Take away the standard reduction potential at the anode. So basically what we're doing here is we're calculating to see what the voltage of this cell would be. So the cathode is going to be negative 0.28 volts. Take away negative 1.66 volts. So we bring in our calculator. 0.28 negative, take away 1.66 negative, gives me a cell voltage of 1.38 volts, and that is the standard cell conditions, so 1 mole per liter at 298 Kelvin. The final thing I want to do is I want to draw out this cell, just so we get some use doing that. So I'm going to write 2 beakers. I'm going to connect them with a salt bridge, probably potassium nitrate as the salt bridge. We're going to put 2 electrodes. One will be nickel and one will be aluminum. We'll connect the electrodes through a voltmeter. Now this is going to be my cathode, and this will be my anode, which means that electrons are produced at the anode through oxidation, and we will have electrons flowing in this direction. Now is really the only place that we actually are going to see the sulfate and the chloride matter. So in this solution, we are going to also have nickel plus 2 and chloride ions. That is where the chloride ions are. They're counter ions, but they will, of course, be in the cell. They'll be in solution. And on the other side, we have aluminum plus 3 ions and sulfates. Now the last thing that we really like to show is we like to show the ion charge. So the positive ions, like aluminum plus 3, are going to move towards the cathode to complete the circuit. The negative ions are going to move towards the anode, so they complete the circuit. And of course, the salt bridge allows that to take place. And we can expect that the voltage that this meter reads to be 1.38 volts. So that's how galvanic cells work. Let's jump down and we'll try another one. So we'll set it up the same way. We have silver metal and silver nitrate. So silver only has 1 oxidation state. It can only be plus 1. Plus 1 electron goes to silver metal. And the other one is iron plus 2 electrons given iron solid. Sulfate is minus 2 as a polyatomic ion, so the iron must be plus 2. That's where we get it, because iron is multivalent. It could be either of them. So we need to go back to the standard cell potential, so we're just going to find them. So we have silver to look up first, and these are alphabetical. So silver is plus 0.799. And that is the standard state reduction potential, which is why we use the little degree sign. The standard state reduction potential for this one, we're looking for iron plus 2. So you got to be a little careful here. There are 2 different irons present, iron plus 2 and iron plus 3. So we got to make sure we get the right one. Negative 0.440, and these are both in the volt. So we look for the most positive one, which is this. The most positive one will be the one where reduction takes place, meaning this is where oxidation takes place. Reduction will take place at the cathode, and this will take place at the anode then. We write out the equation. E cell is equal to the standard state reduction potential at the cathode. Take away the standard state reduction potential at the anode. So plus 0.799 volts, take away negative 0.440 volts. 0.799, take away 0.44. 1 point, let's round it off. So the standard cell potential is 1.24 volts at 1 mole per liter, which is where that 1M factors in. So we draw out the cells again. 2 half reactions. Separate them by a salt bridge. Fill the salt bridge with potassium nitrate. Put your electrodes in. We have a silver one. We have an iron one. Connect your electrodes with a wire. Fill in the rest of your solution. So I have nitrate. I have silver plus 1. I have iron plus 2. I have sulfate minus 2. The cathode is where silver is, so that will be the positive one. Anode. Electrons will always be pushed away from the negative one, so electron flow will be that way. The negative ions will go towards the anode, and the positive ions will go the other way. And that's how we do E cells.